Hey everyone, welcome back and welcome back to my fifth video of my calculus playlist, where today I'm going to be introducing integrals, how they work, and how they actually connect with derivatives in calculus. So I think to best understand integrals, and before we actually dive into some examples and the formal definition, let me just write this up on the top of the screen here. Integrals, calculus lesson 5. Now, before, again, like I said before, we actually start talking about what integrals actually are and how they actually work, let's go ahead and look back at our definition of derivatives, right? We can expect derivatives to be d over dx when we're taking the function's derivative with respect to a variable or input variable x of a function f of x. This can also be expressed as f prime of x. So let's take a really quick example. Let's say we wanted to find the derivative, or d over dx, of f of x, where f of x is equal to x squared. A simple parabola. I could graph this. It's really just a parabola, look something like this. Oops. Okay, let me just erase that real quick. It looks going to be something like this on the Cartesian plane. A domain of all real numbers and a range of y is greater than or equal to 0. But that's just how the parabola would actually look. It's simply a parent function for a parabola. And let's say we wanted to take the derivative of x squared, right? Well, applying our power rule of derivatives, we'd see that this is equal to 2 times x to the power of 2 minus 1, which simplifies down to simply just 2x. Okay, that's great. So we know that the derivative of f of x, or x squared, is equal to 2x. Now, what does that have to do with integrals? Now, we just calculated this simple derivative, right? We're simply just actually calculating the derivative of x squared. Now, I'm actually going to first initialize or introduce the formal notation of integrals. You've probably seen this notation somewhere if you've seen some advanced math problems ever. You probably don't know how to solve it just yet, otherwise that's probably why you're watching this video. But the way integrals actually work is they're going to look something like this. And I'm a very bad drawer, so don't take this for literal. But this is kind of the simple notation for integrals. And after this integral, we have the function that we're actually trying to integrate, right? The function that we're actually trying to find the integral for. So we're going to have the integral symbol. We're going to have f of x, our function. And then after that, we're going to have a dx attached to it for most of the time. And what this really means is we're simply just integrating our function f of x, and we know that with this integration symbol, with respect to our variable input x. Okay, so essentially the integral that we're actually calculating our function of is going to be with respect or for our input variable x. That's with respect to x. That's the literal definition of dx that we actually put after a function when we're integrating such functions. Now let's try to apply this to x squared. So let's say we wanted to find the integral of x squared, as f of x, with respect to x, so dx. Well, what does this really mean? Well, when we say that we want to find the integral of a function, this is also known as trying to find the antiderivative of a function. And the reason why is because when we want to find the integral of a function f of x, we're simply just asking ourselves, what function do we need to take the derivative of to get a result of that function x squared? So let me actually rewrite this to be 2x, just so it's a little bit simpler of an example for you guys. Okay, so what this is really saying is that we're trying to find the integral of 2x with respect to x dx. And what that really means is that we're asking ourselves, what function do we need to take the derivative of to get 2x, or which functions, plus a plural, if you guys can, that's a little bit ambiguous, just interpret it how you'd like. Which functions, or what function do I need to take the derivative of to get a result of 2x? This is where we're simply just differentiating functions. This is where we're anti-differentiating. The reason why is because here we're not trying to find the derivative of 2x, we're trying to find the function that has a derivative of 2x. Okay, that's what this integral symbol really means. That's why they're known as antiderivatives, right? That's basically how that actually works. Now, we know off the bat, well, if I take the derivative of x squared, I get a result of 2x. So can I say that the answer to this integral of 2x is simply equal to x squared? Oh yes, that's true, right? The antiderivative of 2x, or the integral of 2x, is equal to x squared, because when I take the derivative of the function y equals, or f of x equals x squared, I get a result of 2x, which is the function that I'm actually trying to integrate, the function or the antiderivative that I'm trying to integrate for, right? Because again, to reiterate, this integral is simply asking us, for the function f of x, what function do we have to take a derivative of to get a result of that function 2x. In this case, if I take the derivative of x squared, I get my result to be 2x, right? That's basically how the integral works. And again, this dx simply is telling us that we're integrating with respect to the variable x. Okay, well that's simple. That's very nice. Now, let's look at some more higher level examples, right? But before we do that, I actually didn't include something very important in this function. To reiterate, we said that x squared was, or rather had, a derivative of 2x, because that's the definition or antiderivative of an integral. Now, I know for a fact that the derivative, rather, let me actually express this a little bit faster here. So x squared, I know for a fact that x squared prime, that's equal to 2x. That's great. That's what we're trying to find the antiderivative for. But applying our knowledge that the derivative of a constant is 0, can't I say that x squared plus 2 and its derivative is also equal to 2x? And can't I say the same for x squared plus 3 and x squared plus even 5 or even 100? Yes, I can. Notice how I have x squared in all of these examples, but I also am adding or subtracting a constant c. So this also would have a derivative of 2x. And the reason why is because when I actually differentiate a function like this constant is going to have a derivative of 0, and so it's going to go away regardless. As long as we have x squared, this constant doesn't actually matter because it's going to go away. So as you can see, x squared plus or minus any constant is still going to have the same derivative result of 2x. And this is where that plus c that I'll explain actually comes into play. We don't just say that the integral, let me actually write it up here, that we don't just say that the integral of 2x, or the antiderivative of 2x, the function that has a derivative of 2x with respect to x, we don't just say that's equal to x squared. Obviously, x squared is a possible result because it does have a derivative of 2x, but so does x squared plus 2 plus 3 plus 100 plus minus 2 plus 2.5 minus 3.6. All of those functions still have a derivative of 2x. And the pattern to note is that we have x squared as our initial term, but we're adding or subtracting some constant. I'm just going to call it c. And that's where that plus c comes into play. X squared plus any constant c, as long as it's just x squared plus some constant c, is going to have a result or a derivative of 2x. X squared minus 2 is if c was negative 2. X squared plus 6 would if c was 6. Any constant that we add or subtract onto to x squared is still going to give us a result or a derivative of 2x, because again, the derivative of any constant, regardless of if it's negative or positive, has a derivative of 0, right? And you may be thinking, well, x squared doesn't have a constant. Well, it does, technically, right? X squared can also be written as x squared plus 0, and the derivative of 0 is simply 0. And so when we're taking the derivative of this is simply just 2x plus 0, or just 2x. That still has a derivative of 2x, just like all the other constants that we can add or subtract onto our x squared term. And so we say that the integral of 2x with respect to x, or the antiderivative of 2x with respect to x, is equal to x squared plus any constant c. Okay, and the reason why you may be thinking, well, what if c is negative? Well, it doesn't matter, right? C can be negative or positive. And so regardless of what it is, as long as it's simply a constant being added or subtracting on to x squared, it's going to have the same derivative as 2x. Okay, well that's nice. That's pretty straightforward. Now let's look at another rather difficult example to see how integrals actually work. So let me actually just scroll right here. Okay, well, now that we've actually got the integral out of the way, now let's have another integral. Let's say we want to calculate the integral or the antiderivative of 3x squared dx. Now, I highly encourage you to actually Google the integral notation or sign, whatever this is, once you're done finishing this video on like Google or whatever browser you're using, because honestly, this is not a good representation of the integral symbol. Just go ahead on Chrome and just Google, okay, integral symbol. I think it's a lot easier to actually understand how it actually looks like. I'm very bad at drawing, so don't take this literally. But let's say we wanted to find the integral or the antiderivative of 3x squared with respect to x. Now let's go ahead and really look at this function here. Well, let's say we had a function 2x squared. To get the derivative or d over dx of this, we'd subtract 1 to our exponent using our power rule. So this would become 2. And then this would become 2 minus 1, right? Note that this is just our initial coefficient, and we're subtracting 1 from our power. That's the power rule. And we're bringing that result down to the bottom. So this would be the derivative of 2x squared, if we bring this down, is equal to 2 times 2 times x to the power of 2 minus 1. We're bringing this 2 down and subtracting by 1. So 2 times 2 is 4, and x to the power of 1 is simply x. The derivative of 2x squared is x. And notice how, when we're taking the integral of a function, it's basically doing the opposite of taking the derivative. When we're taking the derivative, we're simply just straightforwardly differentiating the function. But when we're taking the integral, we're trying to find the antiderivative. It's literally the inverse or opposite of the derivative, the integral. Right? Because we're taking the antiderivative. Instead of asking us what's the derivative of 3x squared, or whatever f of x we're taking the derivative or integral of, we're asking ourselves, what function do we need to take the integral of to get f of x, instead of what is the straightforward differentiation of f of x. And we have to apply that kind of opposite logic or inverse logic when we're looking like power functions like this. Now, let me quickly erase this. So the way this would actually work is, okay, we have 3x squared. Let me write that down here as well. We're trying to take the integral of that. And in this case, instead of using our power rule for differentiation, since this is integration, it's literally the inverse or the opposite of that, we're going to use the reverse or the opposite power rule, where instead of subtracting our exponent by 1, we add it by 1. And instead of multiplying that result by our coefficient, we divide that exponent result by a coefficient, right? We're literally just doing the opposite or the inverse of what we do with differentiation when we're taking the derivative of functions. Because again, we're not trying to find the derivative of 3x squared. We're trying to find what function we can, or which functions we can take the derivative of to get a result or derivative of 3x squared, which in this case is our f of x. So instead of subtracting 2 our power by 1, we add 1 to that power. So this becomes 3. This is 2 plus 1. And 2 plus 1, we know, is simply just 3. Right? I'm not going to simplify it just yet. I just want to show how this actually works. So we have 2 plus 1 is 3. And we take that result after adding 1 to the exponent. And instead of multiplying by our coefficient like we do in differentiation, we have to divide that by our coefficient like we do for integration. That's literally the inverse of derivatives, right? Let me actually write that big note here. Integrals are literally the literal opposite or inverse operation of derivatives. That is a very important thing to note here. Now, going back to our original integration problem, okay, well, we've added 1 to 2, so now we have x cubed. But now we actually have to divide that result of 3, our result power, by our existing coefficient. Well, 3 divided by that result 3 is simply 1. So theoretically, this is actually 1 times x cubed. But we all know that 1 times anything is just that thing itself. So this is simply equal to x cubed. And believe it or not, that is the integral of 3x squared. But again, we're missing something very important here. X cubed, sure, when I take the derivative of that, sure, it is 3x squared. But what about x cubed plus 2? Well, when I take the derivative of x cubed plus 2, it becomes 3x squared plus 0. That's still 3x squared. Again, the derivative of a constant is 0. X cubed plus 5 is also still a derivative of 3x squared. And that's where, again, our plus that constant c comes into play. The derivative, or the integral, or the antiderivative of 3x squared is not equal to x cubed. That's very important to note. It's not equal to x cubed, or rather, it's not only equal to x cubed. It's formally equal to x cubed plus any constant c. This is the true integral of 3x squared. That is very, very important to note. The antiderivative, or the integral of 3x squared, is equal to x cubed plus c. Not just x cubed, but rather x cubed plus c. Now let's move on to the formal definition of integrals. Okay, so let me actually zoom out here. Well, you guys have probably seen integrals and why they're used. They're basically really popularly called integrals finding the area under a curve. You've probably heard of that notation, or rather that sentence as well, about integrals, and that is completely true. Integrals are very important and used to get the area under a curve of some function f of x. So, now let's actually go back to that original example where we have x squared. Well, the derivative, or rather, we have the integral of f of x. In this case, let's just say that's going to be 2x, rather. And we're taking the integral of that with respect to x. Well, we all know that this is simply just x squared plus c, right? X squared plus any constant c. But this is where actually we're trying to find the area under a curve. So let me actually just area under curve. Okay, so when we're trying to find the area under a curve of a function, we actually need the interval of the basically we need the interval of where we're actually trying to find the area under the curve for. And for our two parameters, if you will, of this integral function, we have our two basically interval endpoints. So it's going to be a and b. And what these a and b variables signify is that they're telling us that we want to find the area under the curve in between the interval a and b of our input variable x. So basically, we want to find the area under the curve for when x is between a and b, right? So if we had something like this, x squared, and we wanted to find the area under the curve from when x is 0 up until x is 2, that would be a is 0 and b is 2, and we wanted to find that, well, we'd apply this integral notation. Okay, so let me erase that, and now let's actually see how that works. Right, we're trying to find the area under the curve in the interval for when x is between a and b. So our interval in this case is a and b. And when I say this case, I really mean all cases. A and b are the general terms for integration, or rather the endpoints of integration for calculus, right? So just know that. It's pretty important to know that. Now, we have the integral from a to b of f of x. In this case, that's 2x with respect to x. A and b are our bounds. Okay, well, first of all, to actually get the area out of the curve, we first have to get the antiderivative, or the integral of our function f of x. So let me just write that, compute. Well, we know that the derivative, or rather the antiderivative of 2x is simply x squared. Okay, that's simple. Now that we've got this x squared, now we need to compute its area under the interval, or rather under the curve from 0 to 2, when x is in between 0 and 2. Well, we literally just have to plug in these endpoints and subtract the corresponding value. So we have to literally just plug in 2 for x squared and 0 for x squared and subtract the amounts. So x squared, when we plug in 2, is simply going to be 4, and x squared, when we plug in 0, is simply going to be 0. So this is literally just x squared when we plug in 2 minus x squared when we plug in 0. We're literally plugging in these two endpoints in for x squared, right? Our antiderivative or our integral of our function f of x. Now 4 minus 0, as you probably know, simplifies down to 4. And believe it or not, that is it, right? The area under the curve of the function 2x with respect to x when x is between 0 and 2, our two endpoints a and b, is 4. That's the area under the curve. And that's it. There's nothing else with that. That's all there is. That is literally just simple integrals and integration with calculus. Okay, now let's look at a little bit harder of an example. So let me grab my pen here. Oops. Okay. Now, what if we wanted to find the integral of x squared dx? And we want to find this, let's just keep it simple for now, in between 0 and 2, right? That's the endpoints of our integral, right? We want to find basically the area under the curve of x squared when x is between 0 and 2. That's our integral of the area that we're actually trying to find the curve underneath for. Well, first of all, we need to first calculate the antiderivative of x squared. Okay, well, let's just bring that down here and look at how that actually works. So, x squared. Now, we're not trying to find the derivative, we're trying to find the integral, also known as the antiderivative. So instead of actually using our power rule to subtract 1 from our power, we add 1 to our power. We literally do the inverse. So x squared plus 1 to our exponent, and then divide the result by our current existing coefficient. Well, I can rewrite x squared to be 1 times x squared. And if I add 1 to it, I get that, and that's equal to 3. And if I divide that resulting power with my current coefficient, I get that this is equal to 1 divided by that result 3 times x to the power of 2 plus 1, which is also equal to x cubed. And simplifying a little bit here, we see that that's equal to x cubed divided by 3. So this is the antiderivative of our function x squared, right? And in this case, since we're actually getting the definite integral, we're not getting the indefinite integral where we need a plus c. We're actually trying to find the area under the curve, and we don't have any other points that we know our integral actually goes through. We will just assume, or we will just say that the definite integral of x squared that we're trying to find the area under the curve for is simply just x cubed plus 3. We're not going to add any plus c for that because we're actually trying to find the definite integral to actually get the area under the curve from 0 to 2. Okay, so let me actually erase that box now. Okay, so that is the definite integral of x squared with respect to x for when we're trying to find the area under the curve. We don't need the plus c. Now let's actually apply our bounds here, right? So we have the antiderivative x cubed over 3, and the formal notation is we kind of just box this and then put our bounds down here. So it's from 0 to 2. That's kind of our interval that we're trying to find the area under the curve for. Now, all we have to do is simply just plug in those corresponding endpoints a and b and subtract their corresponding values into our antiderivative. We don't plug it into the original function and compute from there, because then this antiderivative would be useless, but rather we plug it into our antiderivative. So, if we plug in 2 for x cubed over 3, we see that this is equal to 2 cubed over 3. And if we plug in 0 for x cubed over 3, we see that this is equal to 0 to the power of 3 over 3, right? And note that we always plug in b first and then subtract that corresponding value from a, right? It's not a minus b when we plug them in. It's rather f of b minus f of a, because of course b is a larger value. That's actually the second or rightmost endpoint of our integral that we're actually trying to find the area under the curve for. Okay, so 2 cubed over 3 is simply equal to 8 over 3. 0 cubed over 3 is simply equal to 0 over 3. This is also known as 8 minus 0 over 3, combining like terms, and this is equal to 8. Okay, that was a horrible 3. Sorry about that. Let me actually 2. And so this is equal to 8 minus 0 over 3, which is simply just 8 thirds. And believe it or not, that's it. The area under the curve from 0 to 2 of x squared is equal to 8 over 3. Right? This is not the area under the curve of x cubed plus 3. That's just helping us find as the antiderivative of our actual area under the curve when we actually take the integral of our original function. But the area under the curve, y equals x squared, from x equals 0 to x equals 2 at all the values in between, is 8/3. Right? We don't have to guess using shapes and approximating the area. This is the main use case of how integrals actually work. So if you guys enjoyed the video today and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.